Hello, everybody. Good morning, good afternoon, good evening, good night. Welcome to our seminar. Today we have as our host Professor Claude Cibils. He will speak on controlling for global dimension. But just a couple of minutes at the beginning of our seminar, I want to make some, how to say, announcement that an active member of our seminar who gave talk in July, Desislava Koshlukova, recently was elected to Brazilian Academy of Sciences. So let's congratulate her for this. I think I'm very glad for her. She deserved. Let's congratulate Desislava. No. Okay, Cibils, you can start now. Okay.
Thank you. So I'm very happy and thank you for the invitation. I'm very happy to be in Sao Paulo. And then I will speak about controlling the global dimension. Controlling the global dimension. So please interrupt me if something is wrong, mathematically, of course, and also technically. So the plan of this talk is I would like to first recall some Hochschild homology. And then I will speak about global dimension, and then about Hans conjecture, which is a very nice conjecture, and then about relative Hochschild homology, also by Hochschild. And finally, I will speak about the Jacobi-Zariski long exact sequence related with the Hans conjecture. So, concerning Hochschild homology, I will consider K a field and associative K algebras with units. So, associative ones, like for instance, the field itself, or a matrix algebra, or some group algebra, or some subalgebra of the matrix algebra. In fact, any finite-dimensional algebra arises this way, as a subalgebra of a matrix algebra. Well, in 1945, Hochschild defined in a very nice paper Hochschild homology. He was inspired by group homology, and he gave explicit complexes with explicit boundaries to define Hochschild homology groups or vector spaces for in any degree positive or zero. Let's see the 0 degree, which is at the basement of the theory. You will understand soon why. Okay, the 0 homology is the quotient of the algebra by the subvector space generated by the commutators. The subvector space generated by the commutators for all x and y, xy minus yx. So caution here, because at the first glance, I think that this quotient is an algebra. This should be an idea. It's not an algebra in general. This is not an idea, no chance. It's just a vector space. But of course, it measures some way the distance to the algebra of being commutative, of course, because this is 0 if the algebra is commutative, So the denominator being 0, you have the zero homology of the algebra is the algebra itself, if and only if it is commutative. The important point here to underline is that, even if it is trivial, is that the zero homology is a functor on the category of algebras. If you have any morphism of algebras, no problem. The commutators goes to the commutators, and then you have a covariant functor. But in contrast with that, the cohomology in degree 0, which is the center of the algebra, as you know, the center is not a functor. Unless your algebra morphism is surjective, the center is not going to the center of A dash if you have a morphism from A to A dash. So the center, which also is a measure of the non-commutativity of the algebra, is not a functor in general. A slight generalization that I will need is that if you consider an A bimodule X, an A bimodule is a vector space with two actions on the left and on the right, which are coherent. If you act on the left and then on the right is the same thing that acting on the right and then on the left. For instance, the algebra itself, since it is associative, it's a bimodule. Then you have the Hochschild homology of the algebra with coefficients now in the bimodule, which this is not surprising. It's the bimodule X, but you make the quotient by the subvector space such a way that the left and right actions on the quotient coincide. XA equals AX in the quotient. So this is a functor on the A bimodules. This is called the coinvariance of X. And it's, of course, if you have a left module over a group with trivial action on the right, this is really the coinvariance of the module of a group action. As you perhaps know, but it is not exact, it is a functor, but it is not exact on sequences, exact sequences of bimodules. And so, of course, you have immediately a theory, which is the Hochschild homology theory, which provides a long exact sequence in case you have a short exact sequence of bimodules, and in all degrees. So, as I said before, Hochschild gave a very concrete complex with boundaries, which are well known now, in order to compute this Hochschild homology. So now I would like to say that MacLean, some years later, proved that in fact this Hochschild homology is in fact nothing else than a Tor functor. A Tor functor, while Hochschild cohomology is a next functor. But the Tor functor over an algebra which is the enveloping algebra, in this context is very simple. It's the enveloping algebra is A tensor A op, such a way that left modules over the enveloping algebra are the same than bimodules. So this is a bimodule here. I should call it X M. And so this is the Tor functor between A itself as an A bimodule and X. So this is not strange because, as I was saying, the H0 is not exact. So you have this derived functor, and this one corresponds to this. Some words, if A is commutative, in case it is commutative, there is a Hodge decomposition of the Hochschild homology. And one of the summands is the André-Quilens homology. And this is related also with a cyclic homology for a non-commutative algebra. In the 80s, Kohns and Tsigan defined cyclic homology, which is a natural receptacle for K-theory, for morphisms coming from K-theory. And they gave a long exact sequence relating the cyclic homology with the Hochschild homology. It is also called the SBI sequence because the letters that we use for the morphism in the long exact sequence are S, B, and I. And if A is commutative, this cyclic homology is related to the Durham homology. And this has been proved by Lode and Quillen in a paper in Mathematici Helvetici. So the nice properties of the Hochschild homology is that it is a derived invariant. What this means, two algebras are called derived equivalent if their category of modules are derived equivalent, not just equivalent. This would be Morita equivalence. This has been proven by Happel and Ricker in 89 and 91. So as an example, first example for the field itself, of course, this is not surprising. In 0 degree, you have the field, because the field modulo the commutators is the field, because K is commutative, of course. But then, as you know, tensoring is an exact functor over vector spaces. So you have 0 in positive degrees, of course. This is quite interesting because then the same holds for the matrix algebra. Because the matrix algebra is Morita equivalent to K. But of course, you can prove this directly because the matrix algebra, all the modules are semi-simple. The functors are exact also. And so the same holds for. But just to mention that the fact that in degree 0, this means the matrix algebra modulo its commutators, you have only K. This is the unicity of the trace form. You can interpret that as a proof, or you can think a trace form is a trace, is a map going to the field, such that it is 0 on the commutators as the trace, and there is only 1 because of that. The trace is there. So another less trivial example is the triangular matrix algebra, which is a subalgebra of the R bar matrices. So its homology in degree 0 modulo the commutators, suddenly you have this R which appears. You have more trace forms. And here you have 0 still in positive degrees. Now, for the polynomial algebra in one variable, you have, of course, in degree 0, you have the polynomial algebra, but also in degree 1. But in degrees greater than 1, you have 0. This is not difficult to prove. Which is much more nice to prove, and is when you have then homology in all the degrees. In every positive degree for the dual numbers algebras, I mean, this is an algebra of dimension 2. You kill x to the square. So dimension 2, they call the dual numbers. Then here you have the first appearance of homology in all the degrees, in all positive degrees. And of course, in degree 0, this is a commutative algebra. So you have this, which is of dimension 2 and dimension 1 in positive degrees. I would like to give also something that perhaps most of you know, but if you have a finite-oriented graph that is a quiver, for instance, this graph with double arrows or something like that, then you can construct an associative algebra out of this. The basis of the associative algebra is all the paths that you can see in the quiver. You have the trivial paths, which are idempotents, in fact. You have the length 1 paths, which are just the arrows, and then you have two length 2 paths, length 3 paths, and here you have infinitely many paths. Not here. Here you have 1, 2, 3, 4 paths. So the path algebra will be here of 4-dimensional and here infinite dimensional. Here also it will be infinite dimensional because of this loop. Then you can compose paths if they are concatenated, and then this gives you the product. And if you cannot compose the paths, you say that the product is 0. So this is a path algebra. And as I just show you, the dimension of the path algebra is finite if and only if you have no oriented cycles. So in that case, you can compute, in fact, the Hochschild homology, and much as before, for some of the other examples, you have 0 in degrees larger than 1. In degree 0, you have k omega, and I will say what is omega, and here k omega positive. So what is omega? Omega is essentially the cycles of Q, but modulo rotation. I mean, I do not want to distinguish the source of a cycle of Q. So, and here the gamma positive are the positive length cycles of Q. Here I am allowing the vertices. The vertices are cycles. Here they are not allowed. Of course, both are infinite, but they are by basis of H0 and H1, respectively. So this was some words about Hochschild dimension, Hochschild homology. So now I would like to speak about global dimension. Global dimension is not about the algebras, but it's about the representations of that, the modules of the. So first, I would like to recall that the projective modules are in some way the easy ones. Projective modules over an algebra are the direct summands of the free ones. Of course, for a vector space, for a field, all the modules are free and all the modules are projectives. So the free ones are the easy ones, and the direct summands of free ones are the projective ones. So for the matrix algebra, all the modules are projectives, in fact. Direct columns, for instance, of the matrix algebra, direct summands of columns of the matrix algebra. Over a path algebra, as I said before, the modules are quotients of projectives by projectives. I mean, they are close to projectives in this sense. They are not projectives, but they are quotient of projective by projectives. So this gives you the idea of a projective resolution of a module M is an exact sequence of modules where M is the problem, and then you try to solve it by a presentation. You have a projective module with an epi, and then the kernel, that means the relations, well, you cover it by another projective one, another projective module, an easy one. And then you have, once again, a kernel, and you cover by projective, you resolve it. So this is a projective resolution, much as with singularities, you solve singularities, where the pi are projective. And this projective resolution, which is perhaps not an economical one, we say that it is of length n if at some point it is zero, the projectives are zero, and for e greater than n, and Pn is different from zero, then this is of length n. So the global dimension of a module is not the supremum, but it's of the projective dimension. And of course, the projective dimension of a module M is the minimal length of the projective resolutions of M. No, I mean, the global dimension of all the modules is the supremum, as I wrote here, of the projective dimension, and the projective dimension of a module M is the minimal length of all the projective resolutions of M. So the global dimension is something about the algebra. And as I said before, since for a matrix algebra, you have that all the modules are projective, the global dimension of a matrix algebra is zero, and the global dimension of the path algebra is 1. If the quiver has arrows, because otherwise it is 0 if you don't have any arrow, if you have just vertices. So I would like to mention here a theorem of structure, which is due to Gabriel. If you have a finite dimensional K algebra, say with K algebraically closed in order to be simple, if the global dimension of A of this finite dimensional algebra is 1, this means that any module is projective or quotient of projective by projectives, then there is a unique quiver, unique oriented graph QA, such that finally the algebra A is Morita equivalent to a path algebra, to the path algebra of the quiver. The quiver is unique and quite often is called the Gabriel quiver of the algebra. It's given, the vertices are given by the simples modules, and the arrows, the number of arrows, is given by the dimension of the xth one between the simple modules. This is the quiver of the algebra. So I want to give you a definition which origin is, the terminology is coming from commutative algebra. We say that an algebra is smooth if its global dimension is finite. Matrices algebras are very, very smooth, and path algebras are one less smooth. Dual numbers, I mean, the example I said before, are not smooth, not at all. Even the trivial module, which is one-dimensional, the simple module has an infinite resolution, and this cannot make shorter. Group algebras are not smooth if G is finite and the characteristic of the field divides the order of the group. Otherwise, they are semi-simple. They are product of matrix algebras. Otherwise, they are very smooth, of global dimension 0. Now, I would like to recall a theorem by Bernard Keller. If you have an algebra of finite dimension over the field, an associative algebra, if A is smooth, then something very special happens with Hochschild homology. It's 0 in positive degrees and is k to the r, as for triangular algebras just before, in degree 0, where r is the number of isoclasses of simple modules. And this is completely coherent with the example I gave you for triangular algebras. So if the algebra is of finite global dimension, Hochschild homology vanishes in positive degrees. The proof of this, uses the cyclic homology, and the long exact sequence of Kohns and Zigan. So we have a confirmation of the theorem by the examples I gave you. For instance, for matrix algebras, there is only one isoclass of simple module, any column. All the columns are isomorphic. And if Q is without positive length-oriented cycles, in order that you have, as I said before, a finite dimensional algebra, if your quiver has no oriented cycles, then you have 0 in positive degrees, and these you have only the vertices, as I said before with the omega. The omega is just here, the vertices. And for the dual numbers, it is not smooth, since the homology is not 0, as I said before, for in any degree. So what about controlling the global dimension? Hans' conjecture came just after Happel's question about cohomology and the relation of the cohomology and the global dimension. Hans' conjecture is about a finite dimensional algebra. Hans' conjecture is that if the Hochschild homology you could prove, or you can see that it is 0 in large enough degrees. This means in all degrees after some n, which can be very, very, very large, of course. Then the Hans conjecture would imply that A is smooth. of finite global dimension. This is a way, should be a way of controlling smoothness. So I recall that smooth means that all the modules are easy in the sense that they have finite projective resolution and there is a bound. Of course, then by Keller, 98, that I just mentioned, in fact, if A is smooth, then the Hochschild homology is 0 in all the positive degrees, just by assuming that it is 0 in large enough degrees. If Hans' conjecture is true, then you have this, that in fact you have an alternative. In other words, for a K algebra, finite dimensional over K, we should have an alternative. So the homology would be concentrated in degree 0. That means concentrated in degree 0, so 0 in positive degrees. Or the Hochschild homology is infinite. You have homology in all positive, in sufficiently large degrees always. For infinitely many degrees, you have homology. This should be the smooth case, and this is the non-smooth case. So there's some history about this conjecture. Of course, Hahn proved the conjecture for monomial algebras, path algebras over ideals generated only by paths. This is the analogous of monomial relations for polynomial algebras. So the ideal is generated by monomials. Here you have just 0 paths in the quotient, and not by linear combination of paths, not by polynomials, if we speak about polynomial algebras. So he proved the conjecture for monomial algebras. Then there is a history that Berg, Madsen, and Erdmann proved the conjecture for several families: Koszul, local, cellular, trivial extensions. And I would like to mention also that much before being formulated in 91 and then in 92, the group Buenos Aires cyclic homology group called Bach, and also Abramov and Viguier-Poirier proved the conjecture for commutative algebras, which are finitely generated, not even finite dimension. So, oh yes, the history is also that Solotar and Suarez Alvarez proved in 2013 for Weil quantum algebras, generalized one. So I would like to speak about the class of finite dimensional algebras which verifies Hans' conjecture. Of course, if Hans' conjecture is true, this class is everything, so it should satisfy a lot of things. So my main purpose is to give some extension of algebras. Extension of algebra, this means a subalgebra of a finite dimensional algebra, and to give conditions on the extension in order to prove that B satisfies Hans' conjecture, if and only if the extension satisfies also Hans' conjecture. The main tool for this is relative Hochschild homology. For an extension of algebras, in 55, then 10 years later, Hochschild defined a relative version of his theory of Hochschild homology. He defined the relative version using, again, a complex, an explicit complex with boundaries. The notation is this one. You have here the relative situation, and X is still an A bimodule. For instance, as I said before, the algebra itself. I would like to stress here that B does not have to be central in A, in this theory and in these extensions. And as I said, again, by explicit formulas, in 0 degree, it is the same than the absolute version, something which has to be remarked. But then in higher degrees, things change. And we would like to warn that this is not relative homology with respect to an ideal of A, but with respect to the subalgebra. This is not the theory considered by Laudet in his book. This is something different. So this was in 55, but relative Hochschild homology, in fact, has not been used since then. This was some sort of example of so what theory. So what theory in the sense that there was no applications and no links, not known links, with the usual Hochschild homology. Not even an exact sequence, nothing to do with that theory, even if it was Hochschild which defined, not a so what theory. If B is separable, in fact, I point out that the Hochschild relative with respect to a separable subalgebra, I mean, a semi-simple subalgebra, if the ground field is algebraically closed for simplicity, then you have the same. But in commutative algebra, for André-Quillen homology, there is a so-called Jacobi-Zariski long exact sequence. This is in the book of André, and he explains why the terminology of Jacobi-Zariski, since this is related with classical criteria of regularity from Jacobi and Zariski. This is in the book of André. So in 2012, Kagan succeeds obtaining a Jacobi-Zariski sequence for Hochschild, but with a central hypothesis, not central, I mean a key hypothesis, is that A over B, the quotient, which is a B bimodule, should be flat, projective, if you want, as a B bimodule. I will provide the general situation soon without this hypothesis of being flat or projective. Projective, as a bimodule implies flat. But first, I would like to mention a theorem that we have obtained with Marcelo Lanzilotta, in Montevideo, Eduardo Marcos, he is here in Sao Paulo, and Andrea Solotar from Buenos Aires, but she's now in China for the moment. Come back to Buenos Aires. So the Hochschild relative homology defined by Hochschild in 55 is the homology of a complex of chains, which is rather special. It has this famous quotient that Kagan requires to be flat. And then it begins like that. And this complex, I call it A over B x, where this x index B is some sort of x by the commutators of the action. By B, x, I recall that x is an A by module, but here you make the commutators only by the action of B. And these tensor products, which appears here, is the tensor product over the enveloping algebra. This is the enveloping algebra. This means that the balancing of the action is inside the tensor product and also outside. You make the quotient by the subvector space generated by all these sort of things. Such a way that you have a vector space here, which is not anymore a B by module, but it's some sort of the cycles of this tensor product. The formulas for the differential relies on the choice of a K section of the canonical projection, but on the choice of a K section, just a K section, because in general, there is no section of anything if we are not making any hypothesis on the extension. And this is quite surprising and even unexpected. This is, in fact, is incredible that you can define a D sigma, which is in fact independent of the choice of the linear section that you choose. They are well defined, even this is unexpected, despite sigma is not a B by module map in general. And at the end, with a lot of computations, you can show that, as I said, the differential here do not depend on the choice of the linear section. This is not only quite nice abstractly, but this implies a corollary. That is, there is a fundamental short, nearly exact sequence of complexes, which here you have the Hochschild complex of A with coefficients in X. Here you have the subcomplex B restricting to B. And here you have the chain complex that I just said before, which was unexpected. And take care, because I wrote here nearly exact. What is the meaning of nearly exact? That means that what happens here is that iota is injective, of course, because it is quite easy to see that this iota is injective. Kappa is surjective in the same sense, of course. Kappa iota, the composition is zero, but there is no exactness. The quotient, the homology of this sequence, the kernel of kappa modulo the image of iota, is in general a non-trivial chain complex. And we will focus on this. The proof relies on the reduced, normalized, unexpected bar relative complex of just before. So this nearly exact short sequence of complexes allows to go to a Jacobi-Zariski long, near exact sequence, and then to relate this with Hans' conjecture. This theorem is also joined with Lanzilotta, Marcos, and Solotar for an extension of K algebras, any extension. In fact, you don't need to be finite dimensional. And X and A by module. there is a long, I'm not saying here exact, Jacobi-Zariski sequence, which is, as you think at the beginning, the Hochschild homology of B with coefficients in X, the Hochschild homology of A with coefficients in X, and then the relative one. Iota gives I, kappa gives K, and then you have a connecting homomorphism going to 1 degree less, the same thing. And it ends, unfortunately, it ends at H1. You have nothing for H0, and this is something which is quite strange, but at the level of H0, there is nothing true. With the properties that it is exact on the red dots. The red dots means that the image of the connecting homomorphism is equal to the kernel of I, and the kernel of the connecting homomorphism delta is equal to the image of K. It's exact only at the red points. The composition is 0, and there is a gap of being exact. The gap is, of course, the kernel of K modulo the image of E, and this gap can be computed. This gap can be computed, and this gives you the complete answer about the relation between the Jacobi-Zariski, the relative Hochschild homology, and the absolute one, between 45 and 55 in terms of Hochschild, in terms of years of Hochschild. And this gap, in fact, we can prove that there is a spectral sequence which converges to the gap. The spectral sequence in page 1, is the Tor PQ in page 1 is the Tor P plus Q, the sum of the indices over the envelope in the algebra of the bimodule X of coefficients with respect to this famous A over B of K-gun. K-gun was assuming that this is flat or projective as a bimodule, but raised to the power P as a tensor product with itself P times over B. And this is for P and Q positive. Positive, this means not on the axis of the spectral sequence, and 0 otherwise. And so we call it long, nearly exact sequence because it is nearly exact and it has a gap of being exact with a description using a spectral sequence. And as a corollary, we reobtain the K-gun result relating relative and absolute Hochschild homology if A over B is flat as a B bimodule, but the above sequence is a long exact sequence, a classical long exact sequence, and is the one obtained by K-gun relating the Hochschild homologies. I would like to note that there is no analogous statement for commutative algebras. Now there is, but there was not an analogous result. And the theorem above provides the general picture of the relation between Hochschild, usual, and relative homology, as I said before. Now that we have this tool this Jacobi-Zariski relative, nearly exact, long exact sequence, we can come back to the Hans conjecture and relating the Hochschild homology and the global dimension. We say that an extension of algebra is bounded if some quite natural hypotheses satisfy. This quotient A over B should be right or left, projective as a B module, not as a B bimodule. This makes a large difference. Just requiring that this is projective on the left or on the right. We ask also in the definition to be bounded that this is tensor important. This means that there exists an n such that the tensor powers of A over B are 0. Tensor powers over B. This is important. Otherwise, it is never 0. But making tensor, in some sense, this means that the quotient or the algebra A has no cycles on B. This is some sort of meaning of this hypothesis. And the other hypothesis that we need is that this quotient A over B is of finite projective dimension as a B bimodule. It is not projective, but it's smooth. The quotient is smooth in a sense. So we have two lemmas in case A over B is right or left projective. Here I put it here in blue. The hypothesis in blue, if it is projective from one side, and if it is finite projective dimension as a B bimodule, the pink hypothesis, if A is smooth, then we can prove using once again the unexpected complex computing relative Hochschild homology, then we can prove that B is smooth. So the fact that A is smooth, and with this hypothesis over B, then this implies that B is smooth. In general, this is not true, of course. If A is smooth, you have a lot of subalgebras which are not smooth. But with this hypothesis, we can prove that this. Conversely, I would say, if you have a subalgebra which is smooth, all the modules are finite projective, bounded finite projective dimension, which is automatic. Bounded is automatic. In fact, all the modules have finite projective dimension, then there is a bound. Then with some hypotheses, we can ensure that A, the larger algebra, is also smooth. And so the hypotheses are, of course, very strong. A over B has to be tensor nilpotent in some sense, no cycles over B, and has to be right or left projective. And as I said, this uses very heavily the relative normalized bar resolution, which was the unexpected one, using a section, a linear section that depend on the section. So a third lemma, which is important for the main theorem that I will say, is that if A over B is of finite projective dimension, smooth in a sense, as a B bimodule, and also tensor nilpotent, the green hypothesis, then you have an inclusion of the Hochschild homology of B inside the Hochschild homology of A, which this hardly occurs, in fact. But just for in large enough degrees. We can show these in large enough degrees. So this means that, in fact, if B is bounded, then the Hochschild homology coincides in large enough degrees. This is also part of the lemma theory. Bounded mean, as I said, three hypotheses: tensor nilpotent, projective from one side, and smooth for A over B. So the theorem that we succeed to prove by Zoom, in fact, with Lanzilotta, Marcos, and Solotar, we used Zoom very heavily during 10 days, as we was planning to be in CIRM at Lumini, and of course this was not possible. And then we decided to force ourselves to have the Zoom open during 6 or 7 hours a day, even if not saying anything. And we worked together, and we succeed to prove this Zoom theorem. So if you have any bounded extension of finite dimensional algebras, I stress that you don't need here the extension to be split. This was a previous result for split extensions, but here no split hypothesis, but of course bounded extension. Then B is in Han class if and only if A is in Han class. So this provides some nice step to prove Han's conjecture. You can reduce in some sense to minimal algebras. Previous results in this direction, well, with Redondo and Solotar, we proved something analogous for these sort of algebras, with triangular algebras, with two algebras on the diagonal and a bimodule on the corner. And previously with Lanzilotta, Marcos, and Solotar, we proved, as I said, for bounded and split extensions. So meaning that there is a bimodule which complements B inside A, as here. I would like to finish with an example of these sort of things. Example of a bounded extension which is not split. Not split. So the ground algebra B is the dark one. I mean, you have three arrows B, C, and D, and alpha, beta, zero relation here. I mean, the algebra B is the algebra of the black quiver modulo the two-sided ideal generated just by alpha, beta. Alpha, beta is zero in the quotient, the path. Alpha, beta is zero in the quotient. And here you do some other relation, which is if you make this path, it's the same than the path alpha, beta, or beta alpha, reading from left to right. So you have a new quiver with one arrow more, the red one, with the red arrow, also the black arrow. So this provides you the algebra A, with making the quotient by I and G, I plus G. So this is an example of a bounded extension. And moreover, you have created cycles, even if A over B is tensor nilpotent at the end. And it's projective from the left, I think. And this is smooth because the algebra B itself is smooth. And so this is an example of a non-split bounded extension where all the theory I gave apply. Okay, thank you very much.
Okay, let us thanks Claude. And now questions, comments, please.
Everything was clear.
It's very, very good talk. I'm very impressed with transparency. Okay, well, some question, please.
Somebody was speaking, I think.
Some questions, comments, please. I just want to say that I was very impressed. You explained so transparently this complicated different things, and congratulations for final results, which looks very nice results, and I believe it's quite profound. Thank you, and congratulations for this to you and to your co-authors. Congratulations, really impressed result.
Thank you.
Thank you.
And somebody considered these notions for, say, for Lie algebras. Do you know? Anybody consider this analogs, kind of analogs for Lie algebras or for other non-associative algebras?
For Lie algebras, probably I'm thinking just speaking, but probably there is also a relative version of Hochschild, of homology, of a Lie algebra. But I don't know. I never thought about that. And but it should be for a sub Lie algebra. There is no reason. And so, moreover, there is a relation between homology of Lie algebras and the Hochschild homology of the enveloping algebra of the Lie algebra. So this should be coherent. So probably there is some relative, certainly even.
There is a difficult that you start with finite-dimensional algebra, but universal algebra, universal enveloping algebra is infinite-dimensional. So maybe
yes,
that's
but
a problem.
in fact, the Hans conjecture is just for finite-dimensional algebras. But the Jacobi-Zariski stuff is for any dimension, You don't need the extension to be of finite-dimensional algebra. So the Zariski theory is okay, should be okay. But of course, Hans' conjecture is only for finite dimension. But you see, a path algebra is infinite dimensional as soon as you have cycles in the quiver. And you can compute Hochschild homology and even relative Hochschild homology.
What is just a second. What is the relation with the finitistic dimension conjecture? Classes that satisfy Hans or classes that satisfy the finitistic?
I think there is no relation with the finitistic dimension conjecture, because the finitistic dimension, I would say that perhaps there is a relation with cyclic homology. The finitistic dimension is perhaps related to cyclic homology, and for cyclic homology, you have a relative version of it, and you have also a Jacobi-Zariski long, nearly exact sequence for cyclic homology. And so this is perhaps in relation with the cyclic homology, the finitistic conjecture. But I am saying this just by, not really by chance, but I never walked a lot on this direction.
I have another question.
Okay, please.
If you look at the group algebras, of course, if group algebras are finite dimensional, you know everything. But let's talk about infinite dimensional with groups that are torsion free even. And I want to ask about the relationship between groups of finite index and the full group. Okay, so the relative version in an infinite setup, but the relativity is finite. So
by our results, you have a long exact sequence, a long nearly exact sequence relating the Hochschild homology of the group algebra, which is in turn related with the usual homology of the group. But at the Hochschild homology level, you have a long nearly exact sequence. And I think that in case, finite index case, as you was mentioning, this long nearly exact sequence is actually exact. I mean, the gap should be zero, because if you have a subgroup, the quotient of the algebras is projective from one side and from the other side also. It's projective as a binomial. You have these two transversals that you can, and so it's finite index. So probably you have a long exact and not nearly exact, a long exact Jacobi-Zariski sequence relating Hochschild homologies, relative one and absolute one. Yeah.
But you know, I mean, this is very nice. You know that it is not known that if you have a torsion-free group and you take a subgroup of finite index and you take a module over the big group algebra, and you know that it is projective over the subgroup algebra, then we don't know that it is projective over the full group algebra. Okay, that's a conjecture, a long conjecture, maybe 40 years.
Yes. Yes. I think
So you
No, these will not show the conjecture, but it would confirm the conjecture, because if it is if you have some projective thing, then the Hochschild homology is 0. Then, but not the converse.
I see.
So I think we could prove that the Hochschild homology is 0, but this is not enough to prove that the module is projective.
I see.
Yeah.
Okay, more questions? Comments?
The comments are that this was a great lecture, as you said.
Thank you.
I agree.
Very
I
much.
agree. Also, really, so clearly explain. Well, at least for non-specialists, you consider you could explain transparently the ideas. So really, thank you very much. Thank you very much, Claude. So
Thank you for the invitation. Thank you.
let us thank Claude again for this very beautiful lecture. And I want to announce the lecture for the next Thursday. The speaker will be Professor Veselin Drensky from Bulgarian Academy of Sciences, and he has a very interesting title, From Diophan Transport Problems from 2016 and its possible solution from 1903 to classical problems in algebra. So very intriguing title. So thank everybody for participation.
Thank you.
And see you the next Thursday in our seminar.
See you.
Bye-bye.
Bye-bye.
Thank you, Claude, very much again.
Thank you. My pleasure.